Hey guys, we're Haley and Alisa, and today we will be explaining the physics of the roller coasters at Great America. We went to Great America over the Memorial Day weekend, and we're excited to go over the physics concepts that make these rides work.
The swings are a perfect example of circular motion, which is the motion of an object traveling along a circular path. An object stays in circular motion as long as it has a centripetal force, which points towards the center, and tangential velocity, which is perpendicular to the centripetal force. In this case, the centripetal force comes from the horizontal component of the tension force, and the initial velocity comes from a motor inside the center of the ride.
Psycho Mouse is the next ride on our list, and it demonstrates Newton's first law, or inertia. Basically, an object in motion will stay in constant motion in the same direction, and an object at rest will stay at rest, unless acted upon by an outside force. The thrill of this ride comes from its jerkiness. When the cart takes a sharp turn, the rider's body hits the wall of the cart because it resists the changes in direction, which causes the rider to feel thrown to the side. Even though the cart changes direction, a force doesn't act on the rider's body until they hit the edge of the cart, which causes the rider to almost fall off the side of the ride, as you see in this photo.
The centrifuge is the perfect way to explain the difference between revolutions and rotations. A revolution is one complete orbit around an external point, while a rotation is a spin around an internal point. While on the centrifuge, the connection point connecting the different carts is revolving around the center while rotating on its axis. The riders revolve around the connection point. This principle is important to physics because there are different formulas for calculating rotation and revolution.
The bumper cars are an example of a partially inelastic collision, where momentum is conserved but some kinetic energy is lost as thermal and sound energy. In an elastic collision, momentum and kinetic energy are both perfectly conserved, so the two colliding objects bounce off each other without losing speed. In a perfectly inelastic collision, when the two colliding objects hit each other, they stick together and their momentum is conserved but not their kinetic energy. When bumper cars collide, they don't stick to each other, but they also don't retain all of their kinetic energy, which makes them partially inelastic. Some of their kinetic energy becomes thermal and sound energy.
When you ride the Railblazer, you feel the sensation of having both weightlessness and heaviness at different points. This is because of a change in the normal force, or the amount of force required to stay in centripetal motion, in bumps and dips along the track. At the top of the bump on a track, the rider feels weightless because the sum of the forces is pointed downwards towards the center of the arc, and the normal force is smaller than the force of gravity in order to stay in circular motion on the hill. At the bottom of a dip on the track, the sum of the forces is pointed upwards towards the center of the arc, so the normal force is larger than the force of gravity, which causes the rider to feel heavier. The force of gravity stays constant because the rider's mass doesn't change, but they experience the feeling of changing weight because their normal force varies. Is a model of the conservation of energy, illustrating how gravitational potential energy is converted into kinetic energy and vice versa as it swings back and forth. At the very top of the delirium swing, all of the kinetic energy becomes gravitational potential energy, and the ride slows down while going up. At the bottom of the swing, all of the gravitational potential energy becomes kinetic energy, and the ride becomes faster.
example of a roller coaster with loops. If you've ever ridden a loopy roller coaster, you'll notice that all modern coasters have loops that aren't perfectly circular. On a perfectly circular roller coaster loop, the radius of the loop is constant throughout the entire ride, which causes a host of different problems. A constant radius means that the force required to stay in centripetal motion stays constant, even as the velocity decreases at the top. This could cause riders to fall out of the loop if they don't have enough tangential velocity. It could also lead to a very uncomfortable ride for passengers, because the g-forces at the top of the loop are high enough to cause injury. Instead, roller coasters use clothoid loops, which look like inverted teardrops and have steeper sides and a flatter top. In a clothoid loop, at the bottom of the loop, the radius is larger than at the top. This shape leads to less extreme g-forces because of the gradual decrease and increase in radius. This also reduces the amount of tangential velocity required at the very top of the loop to stay in centripetal motion and decreases the chance that any riders fall. Thank you for watching!